All right, now we're going to be looking at speed versus velocity, and here is a segment from our New South Wales syllabus. So let's see where these terms show up in this syllabus here. We can see we're still talking about scalar and vector quantities. Speed is scalar and vector is velocity. We're talking about analysing motion, speed and velocity here. We're going to be looking at these equations not too far off, okay? But over here we're talking about velocity as well. So we have to understand the differences between these and how we can calculate them. If we have a look at our space shuttle here, or any rocket that wants to leave the Earth has to reach a specific speed to break free of the Earth's gravitational pull. We call that the escape velocity, the velocity at which an object must have to completely pull away from the gravitational attraction of the Earth. And they have to reach speeds of 11,200 meters per second. That's 40,000 kilometers or so an hour, which is extremely fast. So that is the speed at which we need to travel to go into orbit. What about a land animal, or I should say an animal? And so we have our peregrine falcon here, which holds the world record for being the fastest animal. And it can travel in its dives at 389 kilometers per hour, which is pretty cool, right? It's flying along and it brings its wings in and comes like a little bullet as it flies downwards, and it's being clocked at 389 kilometers per hour. Well, when we're talking about humans skydiving and falling to the Earth, they will fall to Earth in lots of different speeds depending upon their body position. Okay, this particular one here is making a very like an arrow-like position, I guess you could say, rather than the typical putting your hands out and floating down. But they can travel like up to 193 kilometers per hour. They can go even faster if they're in a position like this, because they've got smaller surface area to pierce through the air resistance or the drag. And then we have our speed of light, right? 3 times 10 to the 8 meters per second. So that's incredibly fast, the light speed. And of course, that is the speed of light in a vacuum. It's pretty close to that in the atmosphere, but it's incredibly fast. If you could travel at that speed, you could travel around the world 7 times per second, which is absolutely mind-blowing. So all of these examples here, we can talk about the speed or velocity, and a lot of times those terms are used interchangeably. Well, when we're doing physics, we want to make sure we're using the correct term in the correct way. When we talk about speed, that's only the magnitude, how fast you're going. It doesn't matter really on a direction. So we call it a scalar quantity, but velocity does have a direction, and that changes every time the body changes direction. So check out this here. I've got the definition of speed is a measure of the distance traveled per unit time, and there's the formula which you've probably seen before, and we can have different units there. So we could have kilometers per hour, we could have meters per second, we could have miles, right, per hour, okay? But let's have a look at this here. We've got our race car track, which is a little bit different to the video I'm going to play in just a sec. But as you can see, as the car's going around this track, it's changing direction. And when it's changing direction, its velocity is changing. So I can move this car at a constant speed around the track, but if its direction is constantly changing, then its velocity is constantly changing. Okay, and so that's something to keep in mind there. And we will learn that when velocity changes, we have acceleration. So think of the car going into and out of a corner. It has to slow down, turn, and then speed up as it comes out. So it's accelerating. It's also changing its velocity as it does that, because it's changing its magnitude as it slows down, but as it starts turning the corner, it changes its direction. So speed is scalar, doesn't matter on the direction, but velocity, it does matter on the direction. Let's have a look here at an example. So here we have a race car. All right, it's moving its way towards the east. It says it's moving along a linear track, so it's straight line, so it's not changing direction at the moment, okay? It's just going straight, but it's a 2.5 kilometer track, and it's got an oil leak, and as it drops the oil on the ground, that allows us to do some calculations. Now this is very similar to a device that we use in the lab called a ticker tape timer, where we have a tape that we pull through a timer, and we have a hammer that goes up and down and makes a little dot on that paper, and this little dot occurs at the same time. So we know that the distance between that represents a certain unit of time, and it's the same distance. So if we have fast speed, we notice that the distance between the dots, right, is larger compared to when we have slower speed. The distance between the dots is smaller. Now, in an exam, if you were asked to explain which tape is from a car doing a fast speed, you can't just say, oh, it's this one here, and the reason why is the dots are far apart. That's not an explanation. That is an observation, right? You just told me that the dots are far apart. Yes, I can see that, and these dots are closer together. But why does the dots being further apart mean that it's traveling faster? Well, this is where you have to use your formula, and you'd say, well, through the same time interval, so this time here and that time there is the same time, right? For the same time interval, this car here is traveling a larger distance compared to this car here. Since it's covering a larger distance in the same amount of time, it must be traveling faster. Okay, so that's the sort of way you have to explain it. Not just this is faster because the dots are further apart and the dots are closer together. You're starting to get there, but that's not an explanation. That's just an observation of the features of the strips. Okay, so let's have a look at a calculation. Here is our formula to calculate speed, distance divided by time. So we've got our distance here, 2.5 kilometers. I've converted it to meters, okay, because our SI units are meters per second. So I've just put 2.5 kilometers as a meter. Then I have my time, and I get an answer there of 58.33 meters per second. Okay, now what about its velocity? Well, velocity is the displacement covered per unit time. Notice this little bar across the S. That bar across the S is now telling me it's displacement, right? So S by itself is speed. S with a dash across the top is usually displacement. You can have different letters for different things. In our particular area where we do it, S is displacement. Some people will use X, and change of X is displacement. That's no problem. That's fine as well. So depending upon the symbols that you use, you just have to make sure you let the person know what the symbol represents and that you're consistent. Okay, so here we're using S for displacement. So displacement divided by time. So the displacement was 2,500 meters. Remember, the displacement is just the change in position of an object. It started here, it finished here, so its position initially was there, its ending position was there, and that happened to be 2.5 kilometers. So I've got 2.5 kilometers as expressed as meters, divided by the time, and look, I get the same magnitude. It's the same magnitude. Yes, good, great. But remember, with velocity, we need a direction. So there's my direction right there, towards the east. Okay, so my coordinate system was that this is east, so therefore that would be west, and then we have north and south, etc. Okay, the object has moved towards the east. If I didn't have that coordinate system, I would have to say to the right of its starting position. So I'm giving a location, a direction. All right, I hope that makes sense to you, and if you like these videos, make sure you flip over to theflipteacher.com, and you can get a lot more there to support your learning, specifically for HSC Science. So over there you can see I've got some clips here of all the study cards that have been produced for the Year 12 course. So the Year 12 course in chemistry and physics are all done. In terms of the videos, I'm still adding bits and pieces, as we always do, to them, but you can see their study cards are all there. Year 11, well, here's a Year 11 study card right here on sort of the material that we've covered recently to do with vectors and scalars. And as you can see, the study cards are graphically engaging. We've got a syllabus dot point, and we've got a video location there as well. So go check those out. Even if you're not part of New South Wales syllabus, you're somewhere else in Australia or around the world, of course, Physics is universal, so you can still use the section of the card. All right, junior is there for year 7 to 10, and then of course primary school science. Always something to learn no matter what part of your journey you're up to. So I hope you enjoyed that, and I'll see you in the next video.